if the camber doesn't change, we can set the initial camber to 0, and then always have good grip due to camber. But is this really true? Let's make now when we do the half car analysis, it is important to realize that we are fixing the chassis and moving the wheels up and down parallel to the chassis. So let's consider what happens during acceleration and braking. During acceleration and braking, you must have seen in most of the vehicles on the road, the during braking, the vehicle tends to dive down. That is, both the front wheels move either up or down at the same point of time as the vehicle is trying to brake. And during acceleration, the vehicle actually squats, which means that either both the wheels move up or down together. So during acceleration and braking, let's see what happens. If you observe the diagram carefully, we have moved the chassis down, and the wheel camber is still 0 because this is a parallel type of suspension with the instant center at infinity. And during a braking, acceleration, or when we hit a bump, both the wheels move up and down together, and the wheels are still perfectly upright. And this also means that there is no grip lost due to camber, which means that this seems to be a very, very nice design. That during acceleration and braking, even if the vehicle moves up or down, or when it hits a bump, the wheels are still upright, and there is no camber change, and we still have very, very good grip, like we discussed a few slides ago. So we can say that this suspension has been optimized for straight line events, because when you're running for straight line, braking, accelerating, hitting a bump, we have very, very good grip. Now let's look at what happens when the vehicle rolls. Let's understand what roll is first. When the vehicle is turning, there is a force acting in the lateral direction. That is essentially the centrifugal force, because the vehicle is turning about a point. This lateral force needs to be reacted by the ground. This is reacted obviously through the wheels. And it causes weight transfer. That means the inner wheel becomes loaded slightly less, and the outer wheel sees more of the load due to the centrifugal force, which also means that the spring corresponding to the outer wheel will compress, the spring corresponding to the inner wheel will expand, and the vehicle will tilt. Let's see what happens when this chassis rolls, as we see in the animation. What happens is that one spring expands, one spring contracts. Depending on the cornering direction, and what we see is that this is the situation where the right spring with respect to the driver has expanded, while the left spring has contracted, and the vehicle is rolling. But this is not what really happens. The tire does not go below the ground, or the tire does not go above the ground. What really happens is that the full vehicle, the tires are still on the ground, but the full vehicle tilts, something like this. And this is not very obvious to see when we do a half car analysis, because the chassis is fixed. But now we can clearly see that as the car is cornering, the chassis is tilting, and because the chassis is tilting, we have some roll, and this roll causes the wheels to tilt slightly. Remember, because the instant center is still at infinity, the wheels are still parallel to the chassis, but the chassis itself has tilted. And this also means that the contact patch is no longer flat, as we had in the braking case. And now the tires have some camber and things, and it has tilted, which also means that we have lost some grip. What does this mean? So although the suspension was very good for acceleration and braking events, this will be slower in corners, because during cornering, when we are producing lateral grip, the wheels have some camber, and the friction circle actually shrinks, and the maximum speed we can take into a corner drastically reduces. So the straight line, another way to put it put this situation is that the straight line acceleration is improved at the cost of some cornering speed if we use this type of suspension. The obvious question is, can we change this? Let's do that. Let's consider the other extreme type of suspension. Let's call it suspension type 2. This type of suspension has the instant center near the CG of the vehicle, or at least at the center of the vehicle. What this does is the wheel now rotates about the IC, which is the arc about the center. So now there is very large rotation of the wheel when the wheel moves up and down, with that is centered around the instant center and moves along the arc that we see on the diagram on the right. So now let's first consider the roll situation. What happens when the vehicle rolls? Like I explained before, one of the tire goes up, one of the tire goes down, and again this time the wheels are no longer parallel to the chassis like we had in the previous case. Now the wheels are perfectly are moving on that arc that we saw in the previous slide, and they are actually turning with respect to the chassis. But and you can see that in this sample animation here, the wheel is turning as the wheel moves up and down. But again, in reality, this is not the situation, and the situation is that the tire is not in the air or inside the ground. They are still flat, and the vehicle itself tilts. And you see that in this situation, we are cornering, and the wheel is rotated about the arc, but it is still perfectly upright with respect to the ground, although it is not upright with respect to the chassis. And this is important because now we can say that we have more cornering grip in this type of suspension. That is because when you are cornering, you have more, the wheels are upright, the friction circle is bigger, and you have more grip. That's why your vehicle has more power. Now again, let's go back to the simulation that the suspension type 2 and do a ride analysis. Move both wheels up and they move along the defined arc, and something like this happens. What has happened here is that the vehicle has moved down, the wheels have moved about the arc, and suddenly we have inclination, and we have lost grip in straight lines. That is because now during acceleration, braking, or when we hit a bump, the wheel is not perfectly upright, and we have camber, and again we have lost grip. Another way to put this is that the extra cornering speed that comes with choosing the choosing this type of suspension comes at the cost of straight line acceleration and braking performance. And this is an example where of the ride analysis where it's really clear how much the this type of suspension, how much the wheel can move around, creating problems during acceleration, braking, and bump. So the question here is, which is the right type of suspension to use? Is it suspension type 1 on the left or suspension type 2 on the right? And this is a difficult question for a suspension designer. How do you decide between these two types of suspension? Is there a right or a wrong? The answer is really no. Both of them are equivalent. They have some advantages, some disadvantages, and it is the choice of the designer to choose which type of suspension he wants to choose here. So he needs other things to. So if you have a vehicle that is pretty good at straight line and you want to improve its cornering performance, maybe you want to tend towards the right design. Or if you want to have a vehicle that performs well in straight line, you can tend towards the left design. The important thing to understand is that these two are extreme designs, and you can find some middle way between these two designs. That is, the instant center need not be so close to the vehicle, nor it needs to be at infinity, and somewhere in between. You can choose where this has to be. How much you gain by moving instant center around? How do you know that? Well, you can't always do these experiments in your head. You need simulation data. So you plot your suspension points into motion view, run the simulation, and get camber plots. When you see camber plots, you will see you can define the arc along which the wheel moves, and then you can clearly see what is working out for you and what is not. What are the things that kind of decide which side of the scale you want to move towards? Well, how much time does your car spend on corners? Is it cornering most of the time, or is it going on straight lines? Does it really lack acceleration? Can you not overtake anybody? If that is the case, maybe you want good acceleration performance. What you're trying to optimize is not your maximum speed, but what you're trying to optimize is lap time. So you can sacrifice the maximum acceleration and get some extra cornering speed if that means that your overall lap time increases. Also, you need to understand that clever designs are possible through minor adjustments in suspension configuration. So you can design a suspension such that by changing some small thing from here to there, your car starts performing. The car that was doing well in acceleration suddenly starts doing well in corners also. So different events can use different types of suspension. So the question is how you can use wheel alignment. That is you can extend this caster analogy to toe, scrub radius, or camber, and make decisions based on data that you derive from these simulations. So this kind of ends the section of the webinar where I'm going to talk about design decisions. And beyond this, I'm just going to take questions and summarize and show you a few more things about hypergraph and HyperWorks MBD, multi-body dynamics, that can help you during your simulation. So another 2 minutes for you to ask questions. Okay, so I have a question that says, is negative camber better or positive? So as we discussed, what we want is the with the absence of any other data, we want the tire to stay upright as much as possible. That is, have zero camber whenever possible. So if your initial camber is say negative, and then as the wheel moves up or down, it your IC is it's placed at a certain place where such that when the wheel moves up or down, your camber turns comes towards zero. Then you would want positive or negative camber. There is no one answer to this question. For example, if you want your car to corner better, you can start with negative camber, and then when you corner, what happens is your outside wheel is going to become more upright when you corner, and your inside wheel becomes more inclined. And what that does is because your outside wheel has more normal force, you can get more grip out of it compared to the inner wheel. So if you have a choice, you want the outer wheel to be having zero camber during cornering, which means that you have a negative camber during other events. But as with more questions in suspension, there is no right answer to is positive camber good or negative camber good. It depends. You will have to do an analysis like we just did for camber through simulation. Someone asked me about roll centers. So the fact is that the roll center is an extension of the concept of an instant center. The instant center is the point where the let me just go back to that slide. Is the point where the extended lines from the front AM and the upper AM and the lower AM meet. And the roll center is simply the line joining this line here. It's simply this line joining the IC to the wheel center, and the roll center is located at where this intersects with the normal. It's actually located at the intersection of the two IC lines, but we can think of this as symmetrical for now. So actually the roll center moves around as the IC moves around. And some people prefer to think in terms of the instant center, and some people prefer to think in terms of the roll center. At least for me, instant center is more of a physical concept, because you can imagine the wheel being turned about this radius, and roll center is a more abstract concept. But you can imagine that if you move the instant center up, the roll center also moves up. If you move the instant center closer, the roll center moves up, and things like that. Also, when the car rolls, it essentially rolls about the roll center. So if the roll center is here, that means the car will tend to rotate about this. So when you're doing analysis to figure out how much the wheel would move up or down by, you can get a good idea from where the roll center is. But the roll center is really an abstract concept, and unless you understand where it comes from and the physical significance of it, it makes little sense. We can always have thumb rules like the roll center should, as far as possible, be below the CG, and whether it should be above the ground or below the ground is also usually talked about, and that kind of determines how your wheel moves, and also how your load is transferred from from the left part of the car to the right part of the car. Okay, so let's get back to HyperWorks and how HyperWorks can help you gather data, plot, and animate things. As we discussed before, we want to use these simulations to understand, to gather as much data as we can, and we want to visualize this data. So we showed you how to visualize the data in HyperView, and how to visualize the plots in HyperGraph. We can implement some, we can also read some suspension data from something called an SDF file. I will show you that. I will show that soon. But I also want to kind of tell you more about the file extensions. If you go to the working directory where you ran the simulation, you will see for every simulation a whole bunch of files are generated. Yeah, like the ones you see here with the same name and different extensions. The ABF file, the SCD file, the log file, the MRF file, the PLT file, and the XML file, and an SDF file. What do these different extensions do? If you look at the HCD, that's essentially the animation. You can always double click on it and visualize the animation that you just saw. The PLT, as I explained, is the plot data, and you can use HyperGraph to plot it like we have done here in this example. You can use the HyperGraph templates to visualize a lot of data at a single point of time. And finally we have the log file that essentially stores some information about the solver. So if you have an issue while you're doing any kind of simulation using motion view, motion solve, and you are contacting us to help us out or understand the problem, please send this log file with that email, attach it to that email so that we understand the simulation that you're trying to do better. Finally, we have something called the SDF file, which can be opened in TextView. TextView is another client in HyperWorks, and you can open. It's essentially a text editor, and you can open really any text file in this. And let's open a document. So let's open. Oops. Let's go to the working directory that I have, Supra demo, and we just ran this model. So let's open the SDF file. So when you open the SDF file, you will see a whole bunch of outputs that are shown here as numbers. So this is essentially raw data of things that you want to plot. Most of these things you can plot, but this also comes up with a few extra information that we have not plotted. Things like tractive force steer, and what might be interesting is roll camber, roll caster, and other things. If you see here, what this means is the wheel displacement is, for example, 0. At that time, the toe in is so much, the camber angle is so much, etc. You can also go to roll caster. This means that let's say ride caster. The unit is degree per meter. This means that for every meter the wheel moves up or down by the ride, the caster moves by 0.4 of a degree. For example, the camber here moves by minus 60 degrees, but we never really move the suspension by a meter. So this is really the derivative of the camber at that point with respect to the wheel moving up or down. This means that if I move the wheel up by say 1 millimeter or by say 10 millimeters, we will have 0.5, 0.6 minus 0.6 degree of camber change. So this is the same data that you are able to plot or view in the animation in raw data format if you are interested in looking at that, and it is sometimes really useful to look at. So again, what does HyperWorks give you? It gives you a whole bunch of files. You can save your motion view model as a .mdl. The .h3d file is the animation that you can see in HyperView. The PLT file is the plot data that is customized for for these half-car vehicle simulations that you can visualize very easily in HyperGraph. And finally, we have the SDF file that I just showed you, where you can see raw data about the suspension in text view. So this essentially ends most of today's agenda. I'm just going to quickly, before I take questions at the end, I'm going to quickly demonstrate to you that what else HyperWorks can do in terms of multi-party dynamics. What I've shown you today is the tip of the iceberg. It essentially is just what is kinematic analysis of half cars. You can extend that to full cars, and we have tutorials uploaded on our website that kind of explain how to do that. So the full, what we can do, we can combine the half car rear and half car for the front and make generate full vehicle and do analysis on them. We can also do on-road dynamic simulation, which means that we can put the full car together, give tires some properties, and we can do simulations like the one you see here. And we can understand the different forces acting on different components while we do this type of simulation, and also visualize how the car would behave and what are the maximum or what are the performance limits of a given vehicle. We can also do load extraction, which essentially means that from motion view you can understand the different forces that the individual components can see. For example, over here we are looking at the forces that the lower control arm sees. We can note these forces down and apply these forces to our FE models to get a better estimate of our factors of safety and the design quality of individual components that comprise the suspension. So you can take data from here, put it in your FE, and make more sense. And this is again just animations of different things that motion view. Motion Solve has been capable of doing. We has been capable of simulating entire truck models, complicated vehicle models, amongst other things. So that is really the end of the webinar for today. And if you have any questions, please go ahead and ask. You want to know about 3D modeling of steering and about upright? I think that was covered in a different webinar, or it was. If you have missed that, on our website we have videos that kind of help you understand the different analysis. Can we trace the path of the motion of the roll center during wheel travel? Yes, right. I think yes, we can. You can. There is a specific output that you can look at. There is an output request you can look at that will that talks about role center. Role inclination. There is a role center. So in the different plots that you saw today in hypergraph, when we plotted those large number of plots, one of the plots is role center. So you can see that here. There you go. Role center location. Oh, that's roles. Yep. So this is the role center height as the wheel moves up and down, and this is how the role center moves laterally. You will see that the lateral force looks lateral movement looks really noisy, but that's mainly because it's moving by only a few micrometers. Okay, but it moves around the longitudinal direction. The height moves around significantly, and you can see plot the role center location very easily here. Things like caster and camber and kingpin inclination, you can see the plots here very clearly. What is the significance? It's very similar to what we spoke about today in terms of camber. So let me give you an example of toe too. Ideally, you would want zero toe, but as your vehicle moves, around, you will see that you actually have a lot of toe. I will give you an example. If you look at this animation, you will see that the toe of the vehicle is significantly changing. You can see that the steering is not moved; it is pointing straight. But still, as the tires move up and down, the toe of the tire changes, and so you can optimize this. So if you can change the suspension points around so that this change in toe is zero even during ride and the roll analysis, which means that you will have better grip. So it's something. So I have shown you today one example of the camber, and it's the same thing you can extend to different things like toe. Similarly for scrub radius also you can do that. Oh yeah. So I think I've covered what is the importance of toe in the previous question. Do we have any more questions? So what is the importance of caster? The various plots you see here, okay, are different things that you can see about your vehicle, and different things have different importance. Now I cannot take you through all 73 things, but caster affects a whole like camber affects things in the front view, caster affects things in the side view. So if your caster is too high, what will tend to happen is that when you turn, the aligning torque or the pneumatic trail, aligning torque of the mechanical train becomes a very large number, and the steering effort that you put in becomes really large. So here we can see that we are having a caster of 8 degrees, which is relatively high, and if this 8 degrees becomes say 18 degrees, the amount of steering effort will continuously go on increasing, and you can see that by plotting steering torque. Since we are not doing a steering analysis, it's not really clear here, but when you do a steering analysis, you will see the effects of caster really significantly, and the major effect of caster is steering torque, but amongst other things. And again, you will have a plot very similar to the toe situation and the camber situation for caster also, and you will have to decide between two extremes of trade-offs. You also have to realize that if you change the caster, it will also going to affect how your toe and how your camber moves around. So if you fix one problem with the camber, you're going to introduce other problems with the caster, and you have to keep iterating until you reach a reasonable solution. There is no perfect solution, but you can keep on iterating to make the solution better and better. And more you understand things here, it is easier. We just did the body roll analysis for camber change, right? So this is an example. This animation that you see right now is an example of us doing a roll analysis. This happens during cornering, and so if you know the speed at which you're taking a corner, and you know the radius of the corner, then you can calculate the centrifugal force acting on the car. If you know the centrifugal force, you can calculate the load transfer. Once you know the load transfer, you can calculate the exact roll that you have in the situation, and then you can accordingly decide what is the right decision that you have to make. Okay, so I will email the links to the templates soon after this this webinar is done. They're on our website. You can go to oterhyperworks.in and you can even Google for Supra approach. It will take you to a link. Okay, so I think that is the end of the webinar, since there is one more question. Oh, you can trace. Oh no, the question: what is the effect of steering camber change during bump? So for a okay, so let me show you more examples. Okay, so let's look at a steering analysis. So what you will see here is a steering analysis, and as the wheels steer, you will see that not only the wheel, the steering, but we are also inducing some camber. If you see in if you see it at this angle, you will see that when the steering is at its limit, there is actually some camber induced at this point of time. So you can plot this by doing a steering analysis and do a similar evaluation of how steering is going to affect the grip that you have. So this is another steering analysis where it is more significant, the camber change. You can really visualize it here. So so not only camber changes during the up and down motion of the wheel, but even when the wheel is steering, the camber can change and change significantly. Well, how much offset you should have? There is again no right or wrong answer to this question. What I would say is, if you can't decide on the offset, try out 3 offsets in a motion view simulation. See which gives you the best results in terms of in terms of the plots that you see, and then choose. So that's the power that motion view gives you. So thanks everyone for attending, and you can send us emails at edu-support@india.altair.com and we will be more than happy to help you out with any issues that you might have with any of these simulations. So hopefully these webinar sessions have been helpful, and these webinars will hopefully also be uploaded on the website in case you want to revise or your teammates want to have a look. Okay, thanks guys.
The organizer